In this video, we're going to use the Ksp of a barium fluoride salt to determine the effect it will have on the change in freezing point of its aqueous solution. As things dissolve into a solvent, those solutes interfere in the solvent's ability to align in order to form a solid. As a result, the freezing point gets depressed. The more solute you have dissolved, the more depressed that freezing point becomes. In this case, we're going to look at a saturated barium fluoride solution to figure out just how much cooler it will freeze at than its original temperature. Well, to do this, we need to know how much material there is. The K of freezing, to solve our temperature change of freezing, it's the K of freezing times the molality. So I need to solve molality, which means I need moles of chemicals. I need to figure out just how much stuff I have dissolved. For this, 1.5 times 10 to the minus 6, my Ksp, well, my barium fluoride solid is in equilibrium with the barium 2 plus aqueous and the 2F minus aqueous. So initially there's none, there'll be some change, we'll gain X and 2x, and we'll reach equilibrium where we'll have x and 2x for our ions. So our Ksp is going to be equal to the barium concentration to the first power, the fluoride concentration to the second power. Barium's concentration is x, fluoride's is going to be 2x, and we get twice as many fluorides than barium's. So whatever they are at equilibrium, I'll have twice as much fluoride as barium. And then that concentration is going to be squared. I'll distribute that square to both parts. What we'll find is that x times 4x squared, which is just 4x cubed, must be 1.5 times 10 to the minus 6. Divide by 4 and then take the cube root. X is going to equal 0.007211, which means I know my molarity of my barium ions and of my fluoride ions. Barium is this much, fluoride is twice this. So in the solution, my total ion concentration is x plus 2x, so it's just 3 times that, 0.0216 moles per liter of ions. So we find our total dissolved molarity. How much is dissolved of stuff? Well, now we need to turn that into molality. Remember that molality is mole solute over kilograms of solvent. Well, we're talking about molarity, so let's assume I have a liter of solution. I'd need a density and whatnot to figure out just how much of it was water, how much was my chemical, except look at my molarity. It's really, really, really tiny. There's practically no weight of ions. So all of the weight really has to come from water. I mean, maybe we're off by a gram, but within our air, all of the weight of our liter must come from water. Well, a liter of water is 1,000 grams. So we have 1,000 grams approximately, which means we have approximately 1 kilogram of water. And how many moles? Well, in that liter, 0.0216 mole of our chemical. Because it is so sparingly soluble, the net effect is that our molarity is roughly equal to our molality. Often, if you have a very soluble salt, this isn't the case. In a liter, you might have 100 grams of salt and 0.9 kilograms of water, and you'd have to adjust and find a different molality. But with very sparingly soluble salts, molarity is roughly equal to molality. Enough that, for our purposes, we can go ahead and use it. So I know my molarity of ions. That should be approximately my molality. Delta T of freezing is going to be negative 1.86 degrees Celsius per molal. My molality is roughly 0.0216, which means my delta T of freezing is negative 0.040 degrees Celsius. Since it's water, zeros are original. We're going to subtract 0.040 and end at negative 0.040. If we'd had something that wasn't water, we'd have a different freezing point to subtract from. In this case, our new freezing temp is 0.04. Not a huge change. There's not a lot of material dissolved, so it shouldn't have a huge change. Generally, sparingly soluble salts only minorly, if at all, noticeably change the freezing points or boiling points of the water they're dissolved in. But we can use our Ksp to determine our concentrations in order to find colligative properties for that solution.